preparing for the PAT course 2023. My name is Kat, my pronouns are she and her, and I am the Physics Access Officer in Oxford, and that means that I run most of our programmes for secondary school students, including all of the stuff to support people like you who are interested in applying to study physics here. This session is being recorded and will be made available to you tomorrow. A quick reminder of the housekeeping rules for those of you joining us on Zoom. You will be able to use the Q&A for any questions that you'd like to be addressed. I'll let you know once that's switched on ready. And you can also access the chat if you want to share answers via the hosts and panelists, or just to chat with each other. But please keep it polite and kind. Do not share any personal details or information, and don't use it for questions. Keep those to the Q&A. If at any point you're feeling unsure or concerned about anything, you can contact our safeguarding lead, Sean, or me. But in the meantime, let's get started. So we've had lots of new joiners this week as we come closer and closer to the PAT. So I'm going to start with a quick reminder of what the PAT is and what this course is. I won't take questions in this section, but if we have time at the end, I'll take them then. And we've also got a big long Q&A session next week. First things first, the PAT is the physics admissions test at Oxford University. It must be sat by all candidates for physics, physics and philosophy, engineering and materials science. Your result on the PAT forms part of the information which admissions tutors use to decide who is shortlisted for interview. And to sit the PAT, your school must register as a test centre and you must be registered as a candidate. In the vast majority of countries, the PAT this year will be in a hybrid format. That means the questions will be on screen and you will have a paper answer booklet that will be scanned and returned through us for marking, and that will be done by your teacher or invigilator. The online test will also include a built-in on-screen calculator, and there is a trial version of this online so that you can practice with it, so you don't need to worry. This webinar, where we are tonight, is part of our PAT preparation course, and we run this on behalf of all of the subjects who require the PAT. The course consists of 8 webinars, the last one is next week, along with problem sets and assignments that we hope provide you with all the information you need to take the PAT, help you prepare for the PAT, and be confident going into interviews if you are shortlisted. The timetable, which is on screen at the moment, is part of the timetable which is at the bottom of every PAT email, and it's always highlighted with where we are in it so that you can follow our progress. In each session, I'll fill you in on any updates or news as we get closer to any key dates. This is our 7th webinar, as I've already said, and you can see us highlighted in yellow on this slide. This week, Justin, a teacher we work closely with, is going to lead a session focusing on circular motion, and I'll share the link to the problems that he is using in the chat once we get started. All of our previous sessions and all the materials that we use are available on our PAT course materials page, which looks like this. Right at the top, there's an introduction to physics problem solving, which is a more detailed look at some of the concepts which we discussed back in our first webinar. Then underneath, all the links to our webinars are clearly labelled and set out in order. The link to this page is also included in all of the emails, so you don't need to hunt around for it now. And it's updated after each session and really clearly labelled so that you can find everything. So that brings us just to a quick reminder that all of the information that both you and your school need can be found on this main page. I'll share this link again in tomorrow morning's email. This is the most up-to-date page, and it's the one that you have to check first for any information that you need. It also has a very useful FAQ page. The most recent update is that registration for schools to become test centres has now closed. If your school is not a test centre, you will need to find another test centre. Your own registration is nearly closed. You have until the 29th of September to ensure that your test centre have registered you as a candidate. We cannot accept late registrations for any reason. So please ensure that you are registered by the 29th of September. There is also a mock-up test format which is available now and is easy to locate via that link at the top. It might sound like it's really complicated, like a huge thing you need to organise, So you need to trust us that your teachers are used to doing this behind the scenes. They do it for all the big exams that you sit, for any other admissions test. Your school will get all of the details. You don't need to worry about it, but do make sure if you're feeling nervous that you have everything in place and your teachers can contact us if they have any questions. The test format, which I also mentioned earlier, is a new one, but it's not a big change. The questions will be really similar to last year's. The syllabus is completely unchanged. We don't want anyone feeling anxious about it, so do make the most of that test format. That is my quick PAT introduction and update. I hope it was helpful. If we have time, I'll take questions at the end, but you are always welcome to email me. And next week, we're going to have a longer webinar to make sure that any final questions get answered. In the meantime, I am now going to stop sharing my screen, hand over to Justin, and enable our chat for the day. So hello, Justin.
Hello, everybody. Thank you, Kat. Just a shout out to anyone who's watching this on YouTube. If you want to be interactive, which I do encourage you to be, please try to get it on the non-YouTube site on Zoom. So you can chat with me and you can type in your answers and I can move you on, because otherwise you might find it a little bit strange and a little bit frustrating. Speaking of frustrating, question 2 in this booklet is really going to frustrate many of you. We'll get to that very soon. So today's focus is going to be on circular motion, and I am actually going to do a little bit of traditional teaching part way through this. We're not just going to look at some problems. I'm going to try and teach you something new if you're unfamiliar with the unit circle. So you've got that to look forward to. But if you can remember all the way back to, I think it was webinar 3, we had lots of fun / evil questions. And I thought as a nice little warm up, we might get back into some of those. So we've got 4 warm up questions for us to crack through. We'll spend no more than about 5 minutes on each of these, and I'll drop hints as and when we need to. So if you have a numerical answer, stick it to me, just the panelists, please don't stick it to everybody in the chat, and I will tell you whether you're good to move on and shout at you if you have not included units where appropriate. Okay, so this is the first problem. You should also have it in your booklet, but if you don't have the booklet, you can just follow it on the screen, and I'll go silent for a couple of minutes and just start monitoring the chat. Ben, move on. Theo, move on. Yes, James. Anima, move on. Alicia, it's a bit longer than that. And like I said, if you're watching on YouTube, this would just be very strange. Lucinda, longer than that. Flo, yes. Liam, yes. Ted, longer. So if you're in webinar 3, Yitian, no, I'm going to want a nice answer, not a crazy fraction. In webinar 3, I believe Rob and Haley were painting my house, and I hired them both to work together. They both were painting at different rates. Karina, that's correct. Move on. This is basically the same kind of question. It's a rate question. So if you can remember how you did the rate question before, this is a little bit of a twist. Ashwin, yes. Sam, yes. And the person who was before, his name has just gone. Toby, no, it's longer than that. Lots of people saying 25 minutes. It's longer than 25 minutes. Don't forget the bathtub is draining at the same time. Remy, units. Matthew, it's longer. Remy, that's better. Move on. Victoria, move on. Yes, Freddie. Okay, I'm going to give a spoiler in about 30 seconds for those who aren't there yet. Ted, come on, units. Oh, Lucinda, show me the working. I like it. Yes. Although, Lucinda, I think there's the working's a little bit incomplete, but I know what you're getting at. Fanshul and Ms. Zahid, correct. Vibhav, correct. Thank you for the units, Ted, but it's longer than that. And whoever A is, that is also correct. So this is the calculation that we needed to be doing. Nice one. Anna and Nick, just getting there before the big reveal. There's not a lot more to reveal. This is basically just the answer now. So you add them as rates, just as we did, just the same as doing resistors in parallel, because it's essentially the rate of flow of current. That's what the resistance is all about. So this is the rate of flow of water, but we've got a nice little negative one there, which you would never get with resistors. So then when we add up those fractions, it's 1/60th. So of course the time is 1 hour. Well done if you got that ahead of time. So question 2, some of you are going to hate this. Yes, Ben. Sam, there's no number. You've just given me a unit. Yes, Sam. And Celia? No, Liam. Abdul? No. It's less than that. Eliza, it's less. Lucinda? Yes. Okay, so those people who have got it, you can be feeling a little bit smug that you've not fallen into the trap that most people will do. James, no, don't give me a fraction. I don't like fractions. It's not maths, it's physics. Is it? Maybe. Okay, Pranshul, I am going to insist on units. Sakib, yes. Yes, Ted and Liam. Okay, Pranshul, I will now accept that answer. Ben, what did I just say about units? Okay, those people, hopefully you've moved on to question 3 if you've got access to the booklet. If I've given you the go ahead, thank you, Ben. You can move on as well. I'm going to give a little bit of a clue for those who are getting frustrated by this. And my clue would be a primary school child could solve this. Not necessarily a Singaporean primary school child. Teniola, there's no units there. Thank you for the units, but it's too big. Okay, I think maybe about 15% of you have solved this so far. Too big, James? Matthew, too big? Okay, Fritz. I don't know where you're from using commas instead of decimal places. But decimal places, but the main thing is units, please. Okay, Frederick, what are you telling me? Oh, I think you've spotted it. So therefore, what is the answer, Frederick? No, Fritz, too big. Yes, Kitan and Frederick, we have realized that the height must be 0 because A plus B actually equals C. So if you were to draw this, you would just draw a straight line or 2 straight lines. So technically the height is 0. I suspect many of you fell into the trap of thinking that you recognize 9, 16, 25 as a Pythagorean triple, but it is not. 3, 4, 5 is not 9, 16, 25. This is not a right angle. Yeah, I'm being very clear. The triangle is not drawn to scale. So there's a warning about stepping back and making assumptions. Don't make assumptions. Okay, let's have a look at question 3. This is a legitimate question for you now. Quite similar to, I think we talked about a pirate and a ninja. If you remember the pirate and the ninja and the parrot flying between them, channel that memory to help you solve this problem. Okay, Sam, let me double check. Yes, I'm happy with that. Move on to the next one. Eliza, yes, happy with that. Liam, close, but not quite right. Yes, Ben? A is a bit more complicated than that. Okay, Liam, you've recovered. Move on. Frederick, give your answer in terms of the variables that I've identified in the final bullet point. Fritz, no. Close, but no. Flo, no. Sion, no, there's no time. I'm not giving you a time. Yitian, that's correct. Kitian, you're close, but not quite there. Maya, I like it. Move on. Sion, no, not quite. So I'm going to drop a little breadcrumb for you. Just like the parrot that was always traveling at the same speed, so is the dog, a nice elastic dog. Gemma, that looks correct. Move on. Ben, you're close, but not there. Although, hang on, Gemma, you've given me 2 answers. Your first answer was correct. Jack, that's correct. Toby, no. Close, but not quite there. Oscar, yes, move on. Remy, if that's a capital D instead of a small d, then I'll accept it. And Matthew, same comment. Okay, Evie, that looks good. Kitty Ann, that's good now. Frederick and Fritz, looks like we're getting it. Okay, coming up to about half of us getting this one correctly. So I'll give you the final breadcrumbs. So you need to be able to work out the time, which we can do from a bit of GCSE physics. And Victoria, you're close. Vibav, you're missing something. I don't think the dimensions work. Sam, yes. G, yes. And Ashwin, yes. Okay, so the answer, I think most of us are getting to the correct answer now, is just 2 big D VD over VC. Okay, so that's the expression that we were looking for. Well done, most of us getting there. Let's open up question 4, a nice probability question. Okay, Sam, no. Flo, no. Theo and Maya, yes. Eliza, no. Anima, Sakib, Catherine, oh sorry, Katerina, all saying the same answer, but it's wrong. Yitian, yes. Sam, no. Liam, yes. Sarah, yes. Pranshul, no. Oliver, no. Victoria, no. Toby, no. Just to speed things up, most of you are saying a half. It is not a half. If you're familiar with the Monty Hall problem or the game show problem, that might help you here a little bit. No, Sam. Oliver, with rounding, is that right? Alex, yes. Ben, no. Thank you, Oliver. Move on. Jack, no. Abdul, no. Yes, it is conditional probability. Fritz, no. Matthew, no. Erin, no. Kitty Ann, yes. Mizahid, no. Matthew, yes, we're there now. Paul, no. I thought I said a moment ago it is not a half or 50%. Priya, yes. Frederick, no. I think another 30 seconds, then I'll drop a breadcrumb. Sam, think about your rounding. But yes, essentially, Teniola, yes. Lucinda, no. Freddie, no. Abdul, yes. James, no. Victoria, no. Yeah, Sam, that's how we round. Flo, yes. Isabella, yes. Ritika, yes. Karina, no. Okay, more right answers than wrong answers. Now I've told you that it can't be a half. Eliza, no. Alicia, sorry. No. Oscar, yes. Okay. So the first clue is, it is more likely that I have selected the white card, because half of the time the white-black card will have its black face up. So that's why it's not a 50-50. Because half of the time I won't be able to select the white-black card and have it white. James, no. Ted, no. Sakib, yes. Anna, yes. Eliza, yes. Okay, Paul, you're giving your answer to everyone. Is Paul correct? Let's have a look. You're kind of ruining the fun if I say one way or the other. But let's do a reveal and hopefully an explanation that we can understand. Okay, so imagine that we ran this game twice, but the second time all of the cards are flipped to the other side. So we're doing it without the cloth. So there are 3 white cards, and it is equally likely that you have selected either of those white cards. However, 2 of them will be white. So if you do select a white card, there's a 2 in 3 chance that the other side is also white. So imagine that you've basically got 6 cards laid out. So you've got 2 copies of the cards. And 3 of them will be white face up, 3 of them will be black face up. And 2 of the ones that happen to be white face up are the cards that are white on both sides. So if you can think about it like that, then you'll realize that it must be 2/3. Okay, so well done if we got that, particularly if we got it early and on the first try. Okay, Paul, you've made your apology. Now just change your little blue box to the hosts, please. Let's do a little bit of teaching. Yeah, fancy a bit of teaching. It's been an inset day today, so I've missed it a little bit. So in maths, you might be expected to memorize this table. Of course, it won't be blank. You'll have to like fill in all of these numbers, which is painful. So I'm going to teach you how to derive this just by knowing that sine 30 is a half. So this is the only one that I really memorize, and everything else I can derive. And when I say everything else I can derive the sine and the cos, but of course I'm expected to know that tan theta is sine over cos, and then these guys, your cosec, your sec, and your cot or cotangent, these are just the inverse functions, so the 1/overs. So if I can do these first 2 rows, everything else I can fill in just by knowing these identities, essentially. So let's think about how we're going to do that. And we need to know 3 principles. Number 1, polar coordinates, which are going to be very useful anyway. If you're doing further maths, you've certainly come across them. But for circular motion, you're going to be using polar coordinates a lot. It's going to be very helpful for you. Pythagoras, which of course we all know, and symmetry, which is going to make things absolutely beautiful. So let's go through and explain this for you. So you'll all be familiar with Cartesian coordinates. So if I've got a point labeled P and I wanted to describe where this is in space with reference to set of coordinates, I've got an origin here and I've got X and Y, these orthogonal coordinates. I could just describe it as X along and Y up, and that gets me that point. I can also describe it using the same origin as a distance from the origin R and an angle that I'm rotating basically from the x-axis around in an anti-clockwise fashion. So if we agree on this, and we call this polar coordinates, if I say this point P has coordinates r theta, you'll be able to put it on this grid. So that's what polar coordinates are. There's also spherical polars and cylindrical polars if you wanted to go 3-dimensional. So instead of having a z-axis, you can have, a z-axis if it's cylindrical, or a phi axis as it rotates out of the plane if you want it to be spherical. And depending on what you're looking at, what the symmetries are involved, then those could be very convenient for you. So hopefully just by applying a little bit of trigonometry, we can see that there's a relationship. If I wanted to know my distance x along the x-axis, so I've got a little right angled triangle here, that is just going to be r cos theta, and similarly my y distance is r sine theta. So that's how I can translate between the two, and I can go backwards if I wanted to, which is a little bit more involved, but we don't need to worry about that for today. So hopefully we can see that, let's imagine that this circle that I've drawn in blue has a radius of 1 meter, centimeter, whatever it is. It's just a unit radius, so we call it the unit circle. So if this is a length 1, then we can see from Pythagoras that 1, the hypotenuse, is going to be equal to x squared plus y squared. But of course, x squared is r squared, which is 1 cos squared theta, or cos theta squared. And y squared is just 1 sine squared theta. So we get this lovely identity, one of my top 10 identities. Basically, 1 is equal to cos squared plus sine squared. And all this is Pythagoras. Lovely, absolutely beautiful. Thought it would be more complicated than that, but it's not. Anyway, so with that in mind, let's go around and fill in this table. So if we look at the 45-degree angles, we've got lovely symmetry in here. So the symmetry of this coordinate x1 and y1, well, x and y are going to be the same length. Okay, so x1 equals y1, whatever it is. So now we can apply Pythagoras to this point. So we know that 1 is going to be x1 squared plus y1 squared. Substitute. So we've got 2 lots of x1 squared, and then we can just rearrange, and x1 is square root of a half, or you can write it in different formats, whichever one floats your boat, which is quite nice. But this you can write in so many different ways. So this is going to be the answer to cos of 45 and also sine of 45. So remember, x was cos theta and y was sine theta. So those are the same. But also from this symmetry, we can follow this around and we can see whatever this angle is, 90 plus 45, so that's 135. We're going to get the same things as we go around. There'll be some minus signs depending on which quadrant we're in, but hopefully, you can identify which quadrant you're in. So we can fill in a lot of the table just from looking at this. If I'm going a little bit too fast, this is recorded and you'll get the link for this, so you can go back and slow it down and see it all again tomorrow, I think. So now, from my knowledge that sine 30 is a half, so I've drawn my 30-degree angle in here. So my y-axis along here, this one's going to be a half, my y1 is going to be a half. Let's plug that into Pythagoras. So as before, we've got the hypotenuse of 1 is equal to x1 squared plus y1 squared, but I know y1 is a half, so I'm adding a quarter onto x1 squared. Let's rearrange that and square root it, and then tidy it up a little bit, write it in this different format. So cos 30 is root 3 over 2. So now let's use a little bit of symmetry again, and we can reflect this 30-degree angle in this dashed 45-degree line, and that will give us 60 degrees. So at 60 degrees, we've basically swapped around these numbers. So this is going to be at coordinate y1, x1, where I've got x1, y1. They've just swapped around at that point. So therefore, I know that sine 30 is the same as cos 60, and similarly, cos 30 is the same as sine 60. And of course, I can carry this on around the circle, doing 120 degrees, 150 degrees, and so on, and just being careful about minus signs. We've also got these points that I've labeled here as 1, 0. So an angle of 0 degrees, x is 1, so cos of 0 is 1, and the y-axis, so sine of 0 is 0. And then the opposite way, at 90 degrees, we've got a 0, 1 there, and then we can go around to minus 1, 0, and then there'll be a minus 1 down at the bottom. So we can fill in all of those common angles, essentially. That's job done. However, if you are lazy, and some people are lazy, some people will call it efficient, but I'm going to call it lazy, you might recognize that there's quite a nice little pattern. And this pattern emerges if you write everything over the square root of 4. If you do that, The signs go 0, 1, 2, 3, 4, 3, 2, 1, 0. Nice. Nice little wave, or yeah, like a little sine wave perhaps going up and down around there. The causes also quite nice, but of course there's a little minus sign that needs to come in at some stage. So that starts the other way around, goes 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4. Okay, so that's another way as a little trick that will help you fill it in, but it doesn't give you a lot of insight or meaning or understanding. So I'm going to call it lazy. But you know, sometimes you need to be lazy. We all are. So we're going to talk mostly about circular motion, but there's 3 things that I learned at university that I wish I had learnt at school or been taught at school. One of them is the unit circle. The other one, well, another one is dimensional analysis. I'm not going to talk about that today, but you know, ask your teachers. Hopefully they're teaching you dimensional analysis. It's incredibly useful. But the third one is that SHM is the same thing as circular motion. It's just viewed from a different perspective. And that means all of the equations that you use in circular motion, you can use in SHM. And waves is also part of this. So the things that we use, the equations we use to describe waves, you can use to describe circular motion, and therefore also simple harmonic motion. It's just the way that you're viewing it from. So these little GIFs are attempting to demonstrate this. Hopefully you'd agree that the little black blob here is going around doing uniform circular motion. Let's focus on the blue blob that's running along the x-axis backwards and forwards. If we just look in this plane now, this x-axis is doing simple harmonic motion. It's going fastest through the middle, the equilibrium position, the origin there. It's slowing down and it's stopping at the ends of this circle. And this is, you know, if I had a mass on a spring, it would be doing this motion if it was horizontally on a smooth table. But in the y-axis, exactly the same thing is happening here. So this could just be a mass bobbing up and down on a vertical spring. This is what it looks like. And then if we track the positions of these blue and red particles with time, which is what we're seeing here on the little sketch, you'll notice that we're getting sines and causes. So we're getting these waveforms. This is the way that we describe it. So all of these things, they are the same. They're just different ways of looking at it. And then we've just got one on the right-hand side that I think is a little bit simpler because it's just showing you the y-axis rather than the x-axis as well. So that's the same thing, just so you can see it a little bit simpler. Absolutely amazing. So when you appreciate that, and I think there's a problem that might be coming up on the problem set about drilling a hole through the center of the earth and falling through it. Keep this in mind if that's a problem on there. If it's not on the problem set, I wrote them a long time ago, so I can't remember. Just look it up. You can find it on YouTube. It's quite a common thing, but it's very wonderful. Okay, I've rambled on for long enough. It's time to go on to some, you know, circular motion problems. So we've got a tricky one coming up, but this one should be quite a straightforward way to get in. So as I swing a pendulum around my head, the closer the string gets to the horizontal. As I swing it faster and faster. I've just been doing this with my class, the whirling bung practical. Maybe you've done it as well. So with the aid of a clearly drawn diagram, explain why it gets closer to the horizontal the faster it goes around. And then the follow-up question is, in order for it to be horizontal, how fast must it actually be traveling? So I'll give you 5 minutes or so. You're not going to be able to show me your diagram, but I'm going to trust you that you are drawing a good diagram. So then if you've got an answer to part B, just pop that in the chat and I'll tell you if you can move on. Okay, I'm just looking in the chat. Okay. Question 4, I'm going to highlight, and if we've got time at the end, I will go back and try and explain it in a slightly different way, if I can think of a slightly different way for question 4. Liam, move on. The next questions are trickier. Sam, yes, move on. Maya, move on. Okay, just to save people typing in the chat, I'm trusting you to draw the diagram. I'm just after your answer to how fast. So you don't need to try to explain part A for me. Yes, Teniola. I love that you're giving me units there as well. Eliza, yes. Emily, move on. So key, move on. Lots of people trying to give me long wordy answers. I'm not after an answer to part A. I won't have time to read them all. Ted, move on. 78 people here. It's a good crowd. Frederick, yes, move on. Oliver, move on. Remy, move on. Ben, move on. Okay, so let's have a look at the diagram that we should have been drawing. So we're breaking up the tension in the string into components, vertical and horizontal. The horizontal is going to be providing you with the centripetal force. But the vertical component has to balance the weight. So as this angle theta becomes smaller, the tension would have to keep on increasing because the sine theta gets smaller and we need T sine theta to equal mg, so we need the tension to get bigger. So therefore we need to be going faster and faster and faster. So if we wanted to make the angle 0, tan of 0 tan of 0 is 0, I think. Sounds about right. We can't really change R, we can't change G. So in order to make this 0, V has to be infinite. So when we do this practical and we say we're going to spin it around in a horizontal circle, it cannot actually be done. You're always going to have some angles, which is why you'd expect to get a very dodgy answer for whatever it is that you're trying to prove. So you'd need it to be going infinitely fast. Hopefully that makes sense. Just give you another 10 seconds to read this if you need to. Okay, let's move on. So let's assume that the Earth is a perfect sphere, radius of 6,400 kilometers, and it's spinning on its axis. A person stands on some weighing scales at the North Pole, and the scales read 800 newtons. So if they were to weigh themselves at the equator, would the scales read more, less, or the same? So that's the answer I'd like you to put in the chat: more, less, or the same. But of course, you would hopefully be able to justify it. So I'm just going to call out the people who I think have a correct answer. So that's Maya, Mirzad. Oh, this is going very quickly. Yitian, Sakib, Anna. Who have I missed? Don't think I've missed any right answers in there. Liam and Frederick, Ashwin, Erin. Yes, correct answers. Abdul, Victoria, yes. Teniola, James, yes. Sam, yes. Oh, interesting. Trying to give me a factor. I'm not sure about that factor though, but we can work it out in the next part of the question. Toby, okay. I think maybe 50% of the answers are correct. Emily, that's correct as well. So we are getting plenty of people going for the wrong answers. Okay, so let's have a look and think about why the answer is less. Yes, Fritz and Alicia, just in time. So if we're at the poles, there is no centripetal force because you're not going around really doing any circular motion. But at the equator, there is a centripetal force because you're going around and spinning around in a big circle of radius 6,400 kilometers every day. So we know that the centripetal force must be the resultant force, and we know that it's pointing inwards. So where does this resultant force come from? There's only two forces acting on the person, and that is their weight, which of course is pointing to the center of the Earth, and the normal reaction force. So if there's a resultant force pointing inwards, that means the weight must be larger than the normal reaction force. Where does that normal reaction force come from? Well, it comes from the scales. You're standing on the scales and the scales are resisting you, pushing you upwards, as it were. So by Newton's third law, if the scales are pushing you upwards, you must be pushing the scales downwards with the same size force, which we know is less than your weight. And that's what the scales do. They read the reaction force that they're pushing back on you with, essentially. So therefore, you will weigh less according to the scales if you're at the equator. So hopefully that makes sense. If not, draw yourself a little force diagram and then it should. So it is different, but how much? What is the difference? So I'm not looking for the answer. I'm not looking for a percentage. I'm looking for a value in newtons as to how much less you would weigh. So what is the difference in newtons? Sam, no. Abdul, yes. I've only got my answer to 2 sig figs, but I think that's probably correct. Maya, yes. Okay, a little chat question. Oh, Celia and Eliza coming up with the same answer, which is close, but it's not what I've got. You might have made an intermediate rounding mistake somewhere. Teniola, yes. Sam, I'm asking for the difference. No to James. Fritz, I want a numerical answer. Don't give me a calculation, please. numerical answer is what I'm after. Liam, I think that's correct. I've got an answer to 2 sig figs written down. Sam, it's too big. Kitty-Ann, don't give me an equation. I'm not working it out. So we've got something in the Q&A. Is it true that centripetal force shouldn't be labelled on any free body diagrams? Would you label a resultant force on a free body diagram? Because that's what the centripetal force is. It's a resultant force. I might label the resultant force. I think I would, and then I would say the resultant force is equal to the centripetal force. Some people may have a personal preference on it, but I don't see it being a particular problem. EV, too big. Diane, yes. Oliver, yes. The speed of rotation, you're on the planet Earth. I'm not going to tell you how long it takes to spin around once. Ben, there's no units, and I don't think you're answering the question. I'm after the difference. Sam, yes. Eliza, yes. Okay. So in the Q&A, why is the force less at the equator? I clearly didn't do a very good job of explaining it. Let's see, now I've got this little diagram. Hopefully this diagram will help to explain it. Ben and Sarah, no, lots of people saying this answer. I wonder if it's the same rounding mistake that you're making. Hopefully you're doing all of the substitutions in the final step and sticking in algebra. Sakib, I'm not liking that power of 10. Kitty-Ann, give me a decimal answer. Don't make me work anything out. And also give me units, please. Anna, yes. Let's see. Hang on, Kitty-Ann, if that's times 10 to the 13, that's craziness. Or minus 13, that's equally, well, not equally crazy. It's less crazy, but no. Okay, so some people apparently assuming G equals 10. A levels 9.81, please. And that might give you the answer of 2.7, which a lot of people are getting. My answer is 2.8. Let's have a look and see how I did it, and hopefully this will answer Freddie's question. So let's have a look at the two forces acting on this person at the equator. We've got their weight, mg, pointing inwards, and we've got the support force at the equator pointing outwards. We know mg is larger because the resultant force is going to be pointing inwards. Okay, so mg minus se gives us our resultant force, which is, of course, the centripetal force. And it's more convenient, I think, to use m omega squared r, because you should know the time period is basically 24 hours. Well, so yeah, we'll assume it's 24 hours. It's slightly less, but we'll go with 24 hours. That works out well enough. Okay, so we can substitute for omega as 2 pi over t. And then if we wanted to work out the normal reaction force, well, that's just our weight. So I've substituted for mg as weight because we're told what weight is. And then I've substituted for m as w over g here. And then we can substitute in the values that we have been given or that we know to work out the difference, because of course the difference we're just going to take it away from the weight, which was the 800 before. So if we work out the difference, substituting in those values, I got 2.8 newtons. So hopefully we can see now from the force diagram why your weight, according to the scales, your weight is still the same in reality, but according to the scales, you weigh less, because the scales are all about this contact force. So let's stick with this theme, but let's imagine that we're in Oxford. Before COVID happened, you would have been in Oxford. We used to do kind of whole day events, and it was great fun because they've got massive blackboards that go all the way up to the ceiling. They've got 3 of them. I think they're still there. Why would you get rid of them? So What would be the value this time on the scales if we were weighing ourselves in Oxford? And Oxford has a latitude of 51.8 degrees. And I'll give you a moment to try to figure out what that means. You will need to draw a diagram. And I'm going to want this answer to 1 decimal place. Thank you to those who have given me an answer already. But in order to check it, I do want it to 1 decimal place this time. Yes, Maya. No, Liam. No, Abdul. Taniola, no. Okay, Oliver, this time I'm after the value, not the difference. No, Abdul. So a little clue before the diagram, you need to consider 3 forces. There is a third force on your free body diagram. Celia, no, too high. No, Sam. Let's have a look at the diagram. So the first thing to realize is that 51.8 degrees means that from the center of the Earth, I can draw this triangle. Yeah, I've drawn a little triangle here to work out a new radius that I'm going to be spinning around. So when I'm at the North Pole, the radius is 0. When I'm at the equator, the radius is 6,400. When I'm in Oxford, the radius is somewhere between the two. So I use a bit of trigonometry to work out that radius. And obviously, if we just added your weight and your normal contact force, then your resultant force must be along this line. But we know that the resultant force is going to be pointing along the line of this dashed radius. So we know that we need another force. And it's going to be a frictional force pointing in this direction. That's the only thing that it could be. So I'm going to give you a bit of time with this. The math is a little bit involved. So I think, Sam, I told you that wasn't correct. I can tell you it is a little bit too low. Okay, who was it? Was it Maya who got it correct straight away? Maya, was that lucky, or do you think now I've given you the force diagram that you were actually doing it correctly? Okay. For those playing along at home, Maya is maintaining that she did it the correct way. I'll give it another couple of minutes to see if we can get some more answers in. Okay, we have the second correct answer. Is it Yitian or is it Sam? Who got the correct answer? It was Sam. Okay, Yitian, you've just changed your answer, but it's still incorrect. It's still too low. Okay. Kitian, it's got to be less than 800. You weigh the maximum, according to the scales, at the North Pole and the minimum at the equator. So we're somewhere between the previous two answers. Okay, Oliver, you're too low though. Larion, I need it to a decimal place before I'm going to say if I agree or not. So answers to 1 decimal place, please. Larion, too high. Mize, too low. Sion, too low. Kitian, far too low. Teniola, too low. Okay, so as we're working this out, hopefully you've drawn yourself a nice free body diagram. So we can break down the components and we can figure out what needs to balance. F should also really be broken down into 2 components as well. I'm not after the difference. People who are giving me the difference, but the difference is wrong. That's too high. Ben, so close, but no. Sarah, no, too low. So let's resolve the forces. This is just maths at this point. Okay, the hard part is figuring out the force diagram and that we actually needed to include friction to make it work. Matthew, what are you doing? Give me units, my man. Okay, so resolving vertically, we can break down S into a sine theta component. F, there'll be a little cos theta component when we play chase the angles and put the theta involved in F. And that's got to balance the downwards component of the weight. So that's our first equation. EV, Matthew, no, too low and too high respectively. It's got to be less than 800. The horizontal parts, we know the resultant force is going to be our centripetal force. So we've got our component of weight that's acting in this direction, mg cos theta. We'll have a component of the friction, and we need to subtract the component of the reaction force, the support force. So if we do that, what can we then do? We can substitute for little r into this equation as r cos theta, and then we can divide through by cos thetas, and it makes it a little bit nicer. Okay, so that's useful. That's quite nice. Then we need to do a few lines of mathematics, and I'll give them to you on the next slide briefly. Watch it in the recording if you want it, but I'm not going to spoil it for you. Our overall expression looks very similar to what we had before, actually, except we've got this cos squared theta that appears. So when that cos squared theta appears, we can substitute in the numbers we've been given, and the answer is 798.9 newtons. Okay, so that's how it's done. This is the physics in the diagrams. After that, it's essentially just the maths. And if you're a fan of maths, how do you know friction is going up the way and not down? If friction was going down, then the resultant force would be acting outwards. We need to get something going inwards because we know that the resultant force is a centripetal force. And if you were to imagine actually being on the Earth and the Earth was covered with ice so that there was no friction, as you were spinning, you would actually slide out and everybody would end up having a big party at the equator. That's where we would all end up. Fun times. There's the math, skipping over it. Watch it on the recording if you need to. Okay, So we made assumptions about the Earth, but actually it's an oblate spheroid. It's not spherical. So it is thicker at the equator than at the poles. And the reason for this is because it's spinning. So this is an effect due to circular motion. This is why it's not a perfect sphere, because of its spin, which is great fun. Anyway, now let's be a bit more realistic. So because of this shape, this kind of like squashed egg shape, do you think that you would still weigh more at the poles than the equator? So I'll just give you a couple of minutes to think about this one. I'm not going to read out what you put in the chat, but I might try and read it because I can imagine this could go quite fast. But there's two factors I want you to think about. So I want to know what those factors are. Okay, so a few people identifying one factor. I'm not seeing the second factor yet. Okay, if you're saying change, that is being very vague. I've told you, I've given you specifics here. So tell me whether things increase or decrease, not just a change. There's an interesting comment here that's just made me do a little bit of thinking. So Freddie has said there's more mass underneath you at the equator, but your radius increases from Earth. So these two factors might cancel out. Even though the mass is now more concentrated beneath you, I think due to the symmetry, you could still assume that all of the mass is effectively acting as a point mass at the center of the Earth. So I'm not 100% confident, but I don't think the fact that there's more mass underneath you is going to have an effect. But thank you for making me think. And if somebody knows that I am incorrect, please feel free to correct me. Because I am not a deity-like figure. Okay, so a few people talking about the speed that we're traveling at. So the two factors, the easy one to think about is the radius. So now we'll be further away from the center of the Earth. So due to Newton's law of gravitation, we can see that our weight should decrease as r increases. So that's one factor. Then a few people now chipping in with a larger radius, you will also have a larger centripetal force, assuming that the period is the same. So therefore, if we've got a larger centripetal force, there's going to be a larger difference between the weight and the normal reaction force. So actually, both of these factors will make us weigh less according to the mass balance. Okay, let's move on to, well, it's called a longer and friendly looking question, but I really enjoy this question. Many millions of years ago, the Earth was spinning much quicker than it is currently. There were about 4 million years ago, there were 20 hours in a day, or maybe it's 400 million. Anyway, there's fossil evidence. 400 million sounds more reasonable. So the Earth is slowing down in its rotation, which is absolutely fascinating. And that's linked to why the moon is moving away at roughly the same rate that your fingernails grow each year. However, that's not the question. Let's go back in time and imagine that the Earth was spinning much, much faster. How short would a day need to be for you to be able to go on holiday at the equator and just float? Not floating like in the Dead Sea, but just floating in the air. So that's the question. It's a fun one to think about. And I need to charge or plug in my charger. Back in a moment. Okay, that was a moment. Okay, give me an answer in hours, please, Sam. That sounds like it could be correct. But I do have my answer in hours, and it's getting too late for me to do calculations. Thank you. Yeah. Ashwin, yes, I've only got my answer to 2 sig figs, but I can believe that is correct. Move on to the next question. How are we doing on time? 5 minutes on this. We should be able to get through all the questions before we end. Maya, yes. Sam, yes. Kitty Ann, yes. Frederick, yes. Okay, maybe this is an easy question. Maybe it's something that is so fun to think about that you've already done it in school or somewhere else. Toby, if you're giving me an answer to the next question, that is correct. Although I don't remember seeing you answer to this question. Diane, yes. Abdul, yes. Sion, yes. Oh, this is too easy. Oh, thank you, Larion. We've got a wrong answer. Yitian, I don't even know what to do with that. That's not a time. Give me a decimal answer in hours, please. Yes, Ben. Fritz, no, it would have to be a shorter time. We're going back in time to when it was spinning around much quicker. Oliver, no. Liam, yes. Yitian, no. Sakib, yes. Remy, yes. Okay, 2 more problems to go after this one. Oliver, yes, I'm happy with that. Okay, I think most of us are getting to it. Some of the other questions are a bit harder. Yes, Oscar. Lovely. So we've already got the expression that we're going to use for this problem, for the person at the equator. And we form this equation. So for them to be weightless, all we need is there to be no contact force. And this kind of leads to weightlessness in space on board the ISS. People say there's no gravity or it's microgravity, which is ridiculous. There's loads of gravity out there. Terrible. I had to tell my nursery teachers off the other day for trying to teach the 3-year-olds that there was no gravity in space. Ridiculous. She then asked me to come in and teach the science lesson to them, which I've refused to do. I can't talk to 3-year-olds. Anyway, so we set S equal to 0. This is lovely. We can cancel out the masses, and then we can just rearrange the t, and then we substitute in the values that we know and love. 1.4 hours, perhaps not as fast as you might think. So spinning around, something like 20 times faster than it currently is, people would be floating around in Africa. It'd be absolutely amazing. Okay, on to the next one. Let's have a look. Our classic thought experiment, Newton's cannon, is firing a cannonball horizontally from a mountain top, and eventually it will fire so fast that it will now go into orbit if we ignore air resistance. How fast do we need to fire this cannonball for it to go into orbit? I do think I've mislabeled these questions. These questions are actually quite straightforward. Certainly easier than some of the other ones, as Liam and Abdul and Sam are proving. Although you're agreeing to 2 sig figs, Abdul, you're giving me a slightly lower number than the others. Maya, yes. Yitian, yes. Ashwin, yes. Move on to the last one. Celia, yes, to 2 sig figs, but we're getting a little bit of variation. I'm confused at what different numbers people might be using. I mean, if I was using a value for a little g, I'd be using 9.81. I wouldn't be using 10. Sam, Sakib, Sion, Matthew, yes. Remy, yes. Okay, let's do a little bit of revealing. I think enough of us have made progress on this. Oscar, units. So the only force acting on the cannonball will be its weight. So therefore, its weight is providing the centripetal force in this case. And that, of course, is given from Newton's law of gravitation. So we set that equal to the centripetal force. And therefore, we can find an expression for V. And then we just have to substitute things in. Mass of the Earth. This might be why we're getting different answers. Did I use 5.97 or okay, 6.0 to 2 sig figs. Fair enough. So we can use that, or set this equal to mg and then rearrange big G in terms of little g and do it that way. If you didn't happen to know the mass of the Earth, it might be given on formula booklets, but it's something that's worthwhile knowing. So what have we got? Oscar's given me the correct answer after a couple of corrections. Evie, yes. Ms. Aid, a little bit too big. And James, I'm not sure what question you're answering with those units. It's not this question, and I don't think it's the next question. Anyway, so the speed that we need to fire the ball at is 7.9 kilometers per second. You fire it that fast and it will now go into orbit when we substitute in those values. So final question from me this session. So let's go to the top of the Burj Khalifa, and we know what 25 degrees north means now. If I were to drop it straight down, I fire a little laser beam, get it set up, and I put a little X where the laser beam pointing straight down makes a spot. But then when I drop the penny, and it's not a windy day, the penny doesn't land on my little X. Why not? And how far away from the X will it land? You will need a good diagram for this one. Toby, it's more. Okay, and Nima, you're on the right track with your thinking. Can you turn that into a calculation? Okay, Toby, you've now gone too far. Wow, Saqib, that is a crazy answer. Too big. Oh, Maya, I think somebody's getting a gold star. Yep, I will accept that answer. Unfortunately, a gold star for me doesn't get you into Oxford. You still have to do the PAT. I could probably get you into Cambridge. I've got lots of contacts there, but not Oxford. Okay, so for those who are in need of some hints, at the top of the Burj Khalifa, you are traveling in a larger radius circle around the globe than you are at the base. So you're actually traveling faster. Oh, Oscar, you've got the same answer as Saqib, which is still, no, very large. Matthew, that's also too large. Liam, too large. Lots of very big numbers coming in here. Of course, it's not what you know, it's who you know, Kat. We all know that. Tongue in cheek. So, another little clue. If you fall from the top to the bottom without sideways air resistance to slow you down, this means that you'll be traveling ahead of the ground as you have an initial horizontal velocity relative to the ground. So work out that relative velocity. We'll have a diagram on the next slide that will hopefully make this nice and clear. But you should have a nice big diagram on your paper already. So the linear velocity at the top is given by this expression where h is the height of the Burj Khalifa plus the radius of the Earth. And there's that cos theta. That's appearing because you're at an angle of 25 degrees above the equator. So at the base, we've got a similar expression, but without that added height. Okay, Ashwin, still too big there. Toby, you're answering to everyone. But no. So everyone knows it's not 0.78 meters. Sorry, Liam, you're getting the same answer. Ms. Aid, no. Toby's quite close, actually. No, Matthew. So the difference, relative velocity, we can work out. And just take away those r's, the 2 pi r cos thetas, they disappear. So the only difference is this h term that's in there. So we're now traveling at the top 5.5 centimeters per second faster than at the base. Remy, I'm going to accept that answer. Liam, I will accept your answer now. Eliza, not quite. I mean, there may be some rounding going on at some point. I've tried not to round during my answer, I don't think. Yitian, that's exactly what I get. So Saqib, closer, but still too big. So now we just need to do Suvat. So we can calculate the time of flight. Diane, correct. Toby, too low. So here's where I've used my 9.81. which I have been encouraging you to use throughout the day. So I get approximately 13 seconds as my time of flight, and therefore now the horizontal component is just speed times time because there's no acceleration. So I made it 70.9 centimeters, and it would have landed ahead of its mark in terms of the way the Earth is rotating. So I'll just show you the diagram for this. So there's my Burj Khalifa, entirely not to scale. But this is a slightly more useful diagram. So we can see that we've got a bigger radius here at the top than we have at the base. So we can work out the difference in those radii. The angle is still the same. But then we just plug in those numbers here. So that's just showing my working for you. So about 71 centimeters is the difference. So Matthew, I mean, I got 70.9. So maybe there's some rounding going on. There's a couple of places where there could have been some intermediate rounding, but I think I saved these in my calculator memory, so I think I was using exact values. It was a long time ago that I did this, so I can't guarantee that, but anyway, it's the method that's important. The final answer may be just worth 1 mark, but if we're doing the correct method, very well done. So gold star to Maya. Very well done to everyone else who got some of the answers correct today. They are very tricky. We are just about, I think, out of time. So I don't know if there's time for me to talk about question 4 or attempt to for anybody who wants to stay on that, but I'll hand back to Catherine for a little bit.
Thank you so much, Justin. If you want to go back to question 4, I am absolutely fine with that. I'm just replying to a question in the Q&A just now. We're not going to do a general packed Q&A this evening, but I will let everybody know that next week we're going to run a slightly longer packed session. So we're going to run from 6:30 all the way till 8:30, so that we have time for our undergraduates to go through their solutions to problem set 4, but also to make sure any last minute questions get addressed. So by all means, head back to question 4, Justin.
Okay, so actually what I'm going to do is try and explain the Monty Hall problem, which is very similar to this. And if we can understand that, then this will hopefully give us a way into this. So in the Monty Hall problem, the scenario is you've reached the final round of the game show. So this is now the prize round. You've beaten off all of your competitors and you have 3 doors. Let's label them A, B, and C. And behind one of the doors is the star prize. You've got a car. You know, you need a car to get to work because public transport is terrible. The train drivers keep going on strike. It's unreliable. You want the car. Behind the other 2 doors is a goat. You don't want a goat because you're humane, so you have to keep it alive. You can't eat it. It gives you no love. And it's, you know, an enormous burden, an enormous food bill. You want the car. So you select a door at random. Let's say you select B. You've got, you know, a 1 in 3 chance of picking the winner at this point. Now, the game show host, who knows where the car is, he opens one of the other doors. Let's say he opens door A and shows you, this is a goat. Okay, good job that you didn't select door A. I'm going to give you the choice. You can either stick with door B, your original choice, or you can switch to door C. And then whatever you pick, that's your final decision. And you either win the car or the goat. So the question is, should you stick or switch? And for many a decade, well, maybe a decade, for a very long time, certainly, even math professors were writing into, I think it was in the New Yorker, this problem first appeared, you know, debating and telling people that they'd got the answer wrong. So the 2 things are, okay, there's 2 choices. It's 50-50. I'm going to go with my gut and I'll stick. However, that is not the best thing to do because the odds on you winning are still a third if you stick, which means if you twist, you've doubled your odds of winning. And the reason why this is because whatever door you pick the game show host can always open another door. One of the other two doors will always have a goat behind it. So essentially, what the game show host is doing is saying you can stick with your original choice, or you can choose the other two, one of which I'm going to take away from you anyway. So if you have the choice of the car being behind one of the other two, that's a 2/3 chance of winning. Another way that people might think, it's still a bit counterintuitive, but imagine that there were 100 doors and only one had a car. You make your selection, you've got a 1 in 100 chance of being correct. The game show host then opens 98 other doors and shows you 98 goats. Are you going to stick with the one that you chose originally, or the one that's remaining? So probability is quite counterintuitive. So it takes a little bit of thinking about what's going on here. And this is one of those kind of questions. So hopefully that's not caused more confusion.
That was perfect. Thank you so much, Justin. Thank you, everyone. I hope you've enjoyed our 7th webinar. We will see you next week, and I will email everyone in the morning with what I believe is something ridiculous like Pat email 24. So thank you very much. Enjoy the rest of your evening. Goodbye, everyone.
Good luck, guys.